Welcome students. Let us see a numerical based on the load balancing concept that we have already covered. So I'm taking the same problem, actually the one which we have solved for stress concept, that is the concrete beam of the size 400 mm by 600 mm is pre-stressed by a parabolic tendon with a pre-stressing force of 1920. We have not changed the values. The rest of the part changes here, though the tendon has a sag of 100 mm at midspan. So first, the major difference is it is pre-stressed by a parabolic tendon. Okay, and it is not a straight tendon, but it is parabolic. So it will look something like this. If this is the beam, the tendon itself that will be provided has a shape of parabola, and it is said that it sags in between at the midspan by 100 mm, and in stress load balancing concept we have taken this as value h. Okay, this particular value is taken as h. This is like this. Okay, so we have to find the extreme fiber stresses by load balancing concept. If it is subjected to, part A is total UDL of 256 kilonewton, which is the same UDL as previous problem, and total UDL of 360 kilonewton. Why we are taking these two values? Just to compare or just to see what is the difference. Okay, how it is changing. So first we will solve part A, and then we will go for part B, that is for UDL of 256 and for UDL of 360. So to start with, we are using the same values. So our area of the section is going to remain the same, that is 400 by 600, that is 240000 mm square. Okay, I'm not repeating how we have calculated all these things. I also is same, that is 72 into 10 raised to 8 mm raised to 4. We have already calculated this in previous problems. H is equal to 100 mm here. That is the sag of the tendon at the center or at the midspan. I can write it as 0.1 meters. Now, for load balancing concept, we have to calculate the upward uniform force. So here the upward uniform force equation is given to us, or we have already done this. P is equal to E into 8H upon L square. We have derived this already, or we have come across this equation when we have discussed what is load balancing concept. Okay, so we will just substitute all the values here. T is 1920, 8H is 0.1. I'm using it 0.1 because everything is in kilonewton and meters. L is 6, that is 6 square. So here we get it as 42.67 kilonewton per meter. So this is the uniform upward force on the tendon. Okay. Now, what is the external UDL? This is the upward force of the tendon. Now we will see what is external UDL here. External UDL is total UDL. First case it is given as 256. So external UDL will be equal to 256 divided by 6. This is the total value. So when we divide it by span, we get it is in terms of kilonewton per meter. This also is equal to 42.67 kilonewton meter. Now the upward force due to the tendon or due to the sag that is provided and due to this pre-stressing force is equal to the external UDL. So here the load is getting balanced in both the directions. Okay, so this is the upward force, this is the UDL which will be acting downwards. So both these loads are already balanced. So with 256 it is a balanced beam. We need not do anything, we need not solve anything further because we know that the load is balanced. Now we will see part B, that is with the UDL of 360 kilonewton. That means when the load is not balanced. Okay, so here after this we can just simply say that Thus, the external load is perfectly balanced. Therefore, there will be no movement, okay, there won't be any movement, and the beam will be subjected to a uniform compressive stress. So what will be there? Only a uniform compressive stress will be there in the beam, that is equal to T by A, and which we have already calculated it as 8 Newton per mm square. So as it is balanced, therefore no movement. Okay, and because there is no movement, what the beam will experience? It will experience pure compression, uniform compressive stress, which is equal to T by A, which is equal to 8 Newton per mm square. Let us see part B here, that is external UDL as 360 kilonewton. So if external UDL is this, we will calculate small w, that is 360 divided by 6, which is equal to 60 kilonewton per meter. Now we will have to see the difference of the internal and external. Internal in the sense, it is the upward force that we have already calculated, P, value of P, which is equal to 42.67 kilonewton meter. So we will have to design this for the difference of 60 minus 42.67. Because there is, in one direction there is 42.67, in the other direction, that is downward direction, 42.67, it will be balanced. So we will have to design this, or we will have to, the stress to be considered will be only for the difference of these two values. So we will find out what is W dash, which is 60, or I will write it as W minus P, which is 60 minus 42.67. This W is upward, this W is downwards and this is upwards. So we're just getting the difference of this. Till it is 42.67, it is balanced. So we need not do anything, there won't be any movement. But this extra thing, or which is equal to 17.33 kilonewton per meter, is going to create extra movement. Okay, so this movement has to be taken care, or we have to find out the stress that will be generated due to this particular movement. So now movement due to the W dash, movement due to W dash will be M is W dash L square by 8. It will be at midspan. It's a UDL acting throughout the length. So it is WL square by 8. So here it instead of W, it is going to be W dash 17.33 6 square divided by 8, which is equal to 78 kilonewton meter. So we have got the moment. Now we can find out the stresses. That is, first we can get F1. There are two stresses. Total F is nothing but F1 plus FB, where F1 is T by A, which is equal to 8 Newton per mm square, and FB is M upon I into Y, where M is 78. So 78 upon 7, this into 10 raised to 6 into 10 raised to 8 into 300. This gives us a value of plus or minus 3.25 Newton per mm square. This means that the final stress F is F1 plus FB, which is equal to 8 plus or minus 3. So, therefore, it is 11, that's 8 plus 3 equal to 11.25 Newton per mm square at top fiber, and 8 minus 3, which is equal to 4.75 Newton per mm square at bottom fiber. That's it. So basically, we have load balancing is, we have to see the movement that is created for the difference of upward and upward force and downward force, and downward force is nothing but the UDL that is acting on the beam. Okay, so we will have to find out the moment for the difference of these two values, and due to this moment there will be stress created, so we will have to find out what is F1 and F2 for the same values. Thank you.